Hello, we are going to talk about the Ashby charts. First of all, what is an Ashby chart? It is a chart in the material selection process in order to select the best material for the specifications that we are going to want to use, or the most effective way the material can be used. There are the charts that we are specifically going to analyze are the modulus density chart, the thermal conductivity versus electrical resistivity chart, the thermal expansion versus modulus chart, and the friction and wear. Before analyzing a chart, we should know that there are three sets of variables that we should consider before any specification. That are the material variables, that are the variables that are inherent in the material, for example, the density, the yield stress, and many others. The free variables, that are the variables that can change during the loading cycle, for example, the force that is applied to a certain object or to a certain material. And finally, the last one is the design variables. These are the variables that we should have into consideration from the design itself. For example, how big or how thick or how much a material can deflect in order for it to be effective for the design that I am going to use. Here is an example of a chart that goes in the way of Young modulus versus the density. And here we can find by the colors how the materials work in order to in the way from how effective it is going to be from the Young modulus versus the density. For example, metals are considered to be way more effective. Thank you.
Hi everyone, I'm going to talk about the modulus density chart, but first we have to know what those properties are. The density is the relation between the mass and its volume, and is due to the space between molecules. For example, we see the polymer foams and some woods are products. We see that the density is lower in comparison with the metals or even ceramics. Is due to the configuration of the molecules. On the other hand, the Young modulus is the zone where the stress graphic presents a linear relation. This is because in this zone the strain is elastic. So if we see this graphic, we see that the metals, the polymers, ceramics, and hybrid have each one the pretty different value of Young modulus. It is due to the difference of molecules. I mean, the space between the molecules in in the polymers, in the rubber for example, is way bigger than any low alloy steel. That implies that for separate those molecules, I mean the molecules of the steel, we need a way bigger force to separate them. For the Young modulus density chart, the first stage implies to see if we are designing stiff ties, stiff beams, or stiff plates. Due to the design you are taking now, we had to take this kind of the relationship. With this relationship, we want to time these graphics where we can see that these lines are parallel within each other. With those lines, with a constant slope, we see what is the best material that we can use. For example, if we are designing a structure, we need a strong material with a high Young modulus if we see that the material, the structure, will be used on the environment, we can use wood because the humidity, so we need some stronger material. Then we see the density, we see that the value that we consider give us a small group of materials. From this group we can choose the best one for us. It will imply if it's cheap or not, if we have a high resistance to the wear, to the corrosion, and then with those criteria we can choose the best material. Thank you.
Hi everybody, I'm going to explain the thermal conductivity electrical resistivity chart. The thermal conductivity represents the heat transfer per surface value and per second when a specific thermal gradient is applied. On the other side, electrical resistivity is the capacity to don't let that the electrical current flow. So in this chart, the relationship between both in metals are proportional to Widman-From's law, because electronic contributions dominate both, but for other class of materials like ceramic and glasses, the thermal and electrical conduction arise from different sources and the correlation is lost. This chart is very useful to determine conductivity properties for metals and non-metal materials.
I am going to talk about the friction. The friction is a force that exists between two surfaces which are sliding or touching, that opposites to the motion, and is generated by the microscopic imperfections. This force is proportional to a normal load, but does not depend on their areas, because the surfaces do not contact completely, but only touch over small patches. The coefficient friction is defined by the following equations, where the coefficient friction is equal to the friction force over the normal load. Thus, in this chart, we can obtain an approximate value for the coefficient friction for different dry sliding materials on a lubricated steel counterface, which the values are plotted on a range for each material. Finally, it's important to mention that the value of the coefficient friction will depend on the type, on the finish of the surface, and the presence of some external agent such as a lubricant that tends to reduce the friction force.
Hello, I'm here to explain the Ashby chart, more specifically wear rate constant and hardness. In different industries that operate with the machinery as large as aeronautic or a small watchmaker, a scenario is present where the component of the machine interact without any tick of lubricants are dry, and eventually deterioration is observed among the component, which is called wear. Example of the application of no lubrication metal contact. Gear system, bolt joint, example flames, assembly with clamps, etc. etc. We can see the diagram of wear rate constant versus hardness. The wear have the measure of the volume cubic meter over the force Newton for distance meter, that it results 1 over megapascals. It should be mentioned that the wear rate is not strictly constant, but remains constant after a period of transition. For the same purpose, material development is necessary to have some universal quantitative parameter for wear. In many cases, it's most relevant to compare the wear properties than only the friction properties. The last diagram that my partners explained for the friction drive, for example, for the manufacture of the mechanical shovels of a medium or low effort wear is required. For the high carbon steel are used. High carbon steel used is there. High carbon is there. This allows to increase the hardness with a thermical manufacture and reduce the wear.
Good afternoon. Ashby, this method is based off the graph. Now on material max in which the certain properties of the material are related in pairs. The method was designed exclusively to be used during the conceptual stage of material selection. The expansion the modulus linear thermal expansion alpha again due modulo E in the expansion as the linear thermal expansion alpha y due modulo E. The charting is in selection material. When thermal stress is important, the control shows the thermal stress generated per Celsius temperature change in a contrast some they define the guideline. Example, polymer and elastomer, metal, technical ceramic, no technical ceramic, foams, the metals and aluminum, zinc alloys, qualjoy, because iron, GFRP. They define the guideline alpha for E, same constant thermal stress per Kelvin. The value the constant C is increased toward to accord right and belong to a certain family of the material, besides of the relationship of most important property that the